Hello students, welcome back. The final section here is on linear approximation, and that's something we did actually a long time ago. It comes from the average rate of change getting closer and closer and closer to instantaneous rate of change, as you can see in this kind of visualization. See this? So we can approximate kind of like this if you stop the limit. You see, in the previous picture, you saw the slope of tangent line being approximated by the slope of secant lines. If you get reasonably close, we can approximate those are about the same, even though not precisely the same. And then that'll be like this. The slope of tangent line here is this quantity on your left-hand side, the derivative. And the slope of secant line is this quantity on the right-hand side, the difference of function value over the difference of x coordinate. Let's go back to the picture. Where's the picture? Yeah. Look at these greens. And this one really far away, so it's not really a good approximation. But around here, looks like there are better approximations here. And slope of secant line, green, and slope of tangent line, red. And algebraically, they look like this. F prime of A versus f of b minus f of A over b minus A. Now from here, flip the denominator to the other side and flip A to the other side. What do we get? We can approximate f of b value, which is typically the future value, with the remaining quantities. That's the linear approximation formula. And some people replace A and B with x and x0 like this. It's the same thing as this. Exactly the same, just more indices. Okay, all right. How about this problem here? Suppose that the speed of a flying bullet is about 700 meters per second right now. It is about 500 meters away from the target. Estimate the distance to the target a half a second later. So, the speed of flying bullet is approximately 700 meters per second. And it is about 500 meters away from the target. Excuse me. The rate of change versus the distance. The rate of change of distance is the speed, so that's the derivative, and distance is the function value. And then right now is 0. And then half a second later, that's what you're looking for. And one more thing, as a matter of fact, speed of this flying bullet is 700 meters per second. And currently the distance is 500 meters away from the target. And distance is actually closing in, getting closer to target. So this should be actually negative 700. Now I think everything is complete. And let's find out the distance. Let's put everything into the linear approximation formula here. Whether you use this form with a and b, or this form with x0 and x, either way it's going to work out the same. So the derivative is negative 700 and then 0.5 minus 0, and then the current distance to this target is 500. And if you calculate that, you're going to get the linear approximation. You're getting 150 according to this. So about a half a second later, the bullet will be about 150 meters from the target. Currently 500. Half a second later, it got much closer. And this is linear approximation because the speed of this flying bullet will change invariably. It'll get a little bit slower. So linear approximation is a relevant concept here. Let's see. What do I have in the answer key? Yeah, same formula, same computation, except that I use x0 first, and then x prime 0 here. I use x of t as the distance. Here I used f of t as the distance. Just change of character, that's it. Enough time for the next problem? Let's try. Find an approximate value of 4th root of 17 through the linear approximation without calculator. Okay, this problem may look stupid because you can always do this kind of computation problem with calculator these days. But 50 years ago, this kind of thing used to be a big deal. Let's see, how do we calculate this thing? Let's consider this. 4th root of x f of 16 is 4th root of 16, and that's 2. 2 to the 4th power is 16. Remember that? 2 squared is 4. 4 squared is 16. Okay, we got that. And then we can calculate the derivative. Let's see, did I do this right? This thing is 1/4 power, so multiply and subtract 1 from the power. Yeah, okay. Alright, this is 1/4, and then 4th root of x to the 3rd power. And you can find out f prime of 16. So 4 times 4th root of 16 to the 3rd power let's continue this in a separate place. And this is 1/4. And then this thing here is 4th root of 16, and then we take 3rd power later. Can you read it? This doesn't have to be that big, so let's move it up to here. And then, what is this quantity? 4th root of 16 is 2. 2 to the 3rd power is 8. So it's 1 over 32. And 1 over 32, you can do this computation without calculator through long division. And if you do that, you're going to get 0.03125. And that's a terminating decimal because this one has only 2 as a prime factor. If a prime factor has only 2 and 5, then we have a terminating decimal. If there are other prime factors, then the decimal expression is not going to be terminal. So we have f prime of 16, the derivative, and then f of 16 there. And from there we can find out, or we can do linear approximation of f of 17. So, excuse me, 4th root of 17 is f of 17, and that's a linear approximation of f prime of 16 times 17 minus 16 plus f of 16. That's how the linear approximation works. Okay, all right, let's continue going over this. F prime of 16, 132, and then times 1, all right, plus 16. Cubic root of 16 is 2. So, and this is 2.03125. 132 plus 2. So that's a linear approximation without calculator. Well, okay, I admit I did use calculator for this computation, but that's just to save time. You can divide 1 from 32. You can divide 32 from 1 and do long division computation, and you can get this. And this is a terminating decimal, so within some time you can do it. And then we get that as a linear approximation, and compare that with far more accurate value, 2.03054, 2.03125. It's pretty good estimation, isn't it? Did I do the same thing here in this computation process? Yes, I did exactly the same. So from there, and then take the derivative, and then f of 16 and f prime of 16. And then linear approximation. Put it in, we get this. Okay, so much for linear approximation.